Today we're going to be studying a kinematics problem using a velocity time graph. So take a second to pause the video here to read over the question, and we'll get right into it once you're ready. Recall that the position from a velocity time graph can be determined by taking the total displacement as the area between the curve and the x-axis. So to determine our position at the 6-second mark, we just have to find the total displacement, in other words, the total area between the curve and the axis, from 0 to 6 seconds. This is a simple problem because we just have simple shapes to use. We have a rectangle and two triangles. Notice that our two triangles have the exact same area, because the base is 1 and the relative height is 10, but one will give positive area and one will give negative area. So they cancel each other out. I'll call area 1 just the simple rectangular shape between 0 and 4 seconds, and we'll calculate that area to be 40 meters. Therefore, if we initially started at the 30-meter mark, and we add the 40 meters we've displaced, we end up at 70 meters. Now, reading from the same graph to determine when we are at rest, being at rest implies we have no velocity, or our speed is 0. Well, that is simply when the velocity, given by the y-axis on this graph, is 0, we find this to be at the points t equals 5 and t equals 11 seconds. For the acceleration at the 11-second mark, we can zoom into the graph and see that we have a simple straight line or a linear function between the 11-second and the 12-second mark. From a velocity time graph, the acceleration will be the slope of the graph. So if we can determine the slope between points 1 and points 2, we have our acceleration. A simple calculation shows that a equals 10 meters per second squared. It also makes sense that we have a positive result, because clearly our velocity is increasing in that 1-second interval. Let's slow things down a bit for question D, no pun intended. I'll quickly highlight the point of interest at 10 seconds, but what I'd like to do first is discuss the overall motion from 5 seconds to 11 seconds. Remember, on a velocity time graph, our curve represents the instantaneous velocity at any moment in time. So, for example, between 5 seconds and 8 seconds, we see our velocity becoming more and more negative. It starts out at 0, half a second later it's at -5, at the 6-second mark it's at -10, at the 7-second mark it's just past -15 meters per second, and at the 8-second mark, it's somewhere around -17.5 meters per second. You can think of this as the fastest it will ever travel in the negative direction. After the 8-second mark and until the 10-second mark, it is still traveling in the negative direction, but the speed at which it is doing that is decreasing. Let's take a quick look at what the velocity vectors of this particle look like on an x-axis over time. So at the 6-second mark, we have a first velocity vector at some speed traveling in the negative x direction. 1 second later, we have a second velocity vector with a bigger speed still traveling in the negative direction. And then at the 8-second mark, we have the biggest speed, velocity vector 3, still traveling in the negative direction. At our moment of interest, at the 10-second mark, we have a fourth velocity vector, smaller in magnitude than v3, which means it has a smaller speed. However, our particle is still traveling in the negative x direction. Now on to part E. In order for this second particle to catch up with the first one, they will have to have equivalent displacements in the 4-second interval. We already know from before that our first particle will have displaced 40 meters, therefore the second one will have to also displace 40 meters. We can use our kinematic equations to solve this, and knowing that it starts from rest, we can simply solve that acceleration is equal to 5 meters per second squared. Putting this onto a velocity time graph, we know that the acceleration must be the slope of the curve. As such, particle 2's velocity will increase by 5 meters per second for every 1 second of elapsed time. Thanks for watching!